hopefully, I hope everyone is doing well as your relatives and loved ones. Okay, Catherine, same thing. She doesn't put her last name. Next time, I will not admit her. Yeah, make sure you put your full name, right? First and last name. Otherwise, I will not admit you, right? Just for safety measure. Catherine, make sure you put your full name. Only Catherine. Next time,
I will. The default.
Yeah, well, just change this, okay? Thank you, Catherine. All right, so some more people. Okay, so let's start here. So once again, good morning, everyone. So we'll start with the questions. So does anyone have questions from the homework? There's just before, I saw here that it says like do 3 and 4 in the handout. I think it was like a 4th handout. I think you did it in the past, so I don't think you have to worry about this. It says also ratio problems. Did I give you a worksheet on ratio problems?
Yeah.
Oh, you did? Okay. All right. So, okay, good. All right. So I can, all right. So I'll just erase this. Okay. So you had, what did you have here? You had on page 184. So any questions? Raise your hand. Yes, Madav?
57 and 55.
So 55 and 57. Okay, good. Any other one? I don't know if I can see. Any other ones you want me to take up, guys? Okay, so let's look at 55. That's the pogo stick. All right, so let me share my screen here. Not my screen, but my iPad. Actually, it's not my iPad. It's my daughter's iPad. All right, so let's see here. All right, good. You should sort of all be able to see that. Okay, so 55, let's see, 50-gram students. All right, so number 55 here. So 50 kilogram, rides on Potosí. If she compresses the spring, 0.20. All right, so that's the amount of compression here, right? On an average bound, the spring is, so you have, we know K. Find our acceleration and bouncing, moving upwards. Use a FBD for the problems. Okay. So this is the, so what we're going to do here, we're going to do the FBD of the person. All right, so the person right here. This is the pogo stick, all right? And this is like a spring of some sort. Of course, she holds, of course, the pogo stick. She got like super long arm. Okay, so let's do the FBD of her. So what's acting on her? Well, you have, of course, the weight, and you have the pogo. And the pogo, it's nothing else but the spring. So, and it's going to be upwards, right? She's on a rebound here, right? And that's all. In this case here, like the normal force is nothing else but the spring force, all right? So it's 90 degrees perpendicular to it. So let's put some direction here. So let's see here, up is positive. You're looking for what here? We're looking for, I don't remember now. You're looking for, okay, you're looking for acceleration. So what's Earth's acceleration? So y-axis, so the summation of the force along the y-axis is equal to the mass times the acceleration. That's what you're looking for. What you have Fs minus the weight equal ma. So this is equal to k delta x minus mg equal ma. And you just plug all the values in and bingo. All right. Is that okay, Madav? You good for number 55?
Yeah. One question I had, like with the pogo stick, when you get to the bottom of the bounce, the pogo stick stops moving when Fs is equal to the weight, right?
Yeah, if so when the yeah, at some point the spring force will be equal to the weight. And at this point, like, it's balanced, but she's just going at the same speed as she would before. But as she compresses more, of course, like, the spring force will be greater and greater. Yeah.
Then
So at first, when she first made contact with the ground, the spring force is less than the weight. So that's why she's still speeding up downwards. At some point, the spring force will be equal to the weight. She's still going to be going downwards. Then the spring force will be greater, and she will still be going downwards. And at some point here, the spring force will be like big enough so that her acceleration will go the other direction. Sorry, she's going to start like going up.
what keeps pushing her downwards though? Because
What
it's
keeps
only her
pushing her
weight.
down? It's the weight that make her like go down, right?
So how come like the spring force can never be greater than the weights?
No, it will. It will. Yeah, absolutely. When it comes up, it will sort of be greater.
Okay.
Yeah, it will. Okay, so let me, Jason. Oh, Jason joined. I guess he's done with his French. Okay, so let's look at number 57. Okay, so number 57. Let's see here. Find the normal force for a crate, a mass being pulled by a spring if the spring is stretched. Okay, so this is what we have here. It's probably on the ground. And there's a spring right here pushing it up. So if you do the FBD of the box, you got the weight, you got the normal force because it's in contact with the ground, and you got the spring force, right? So once again, let's put this like positive right here. And so what you're looking for this. And you have to assume, of course, that the box is not moving. It's not yet moving, all right? It's not yet moving. So if it's not yet moving, then the forces are all balanced. So it's going to be 0, right? And so what you have here, you have Fs plus the normal force minus the weight. So you're looking for the normal force. You bring this on the other side, and it becomes like W mg minus Fs. And then I guess you're given all the other information. Yeah, so you're given delta x, right? You're given delta x, which is 1.55 meter, and k as well. And you just plug this in, and you find the normal force. Are you good? Madav, are you good?
Yep, thank you.
Okay. Anyone else? How do I put this on the top here? I don't know. What does it do if I do this? No, it's just one. Sorry, I'm just talking to myself here. Okay, so any other questions? There was one question here that asked you, like, how much would it need, I think, like a spring force, like, to balance your own weight? Of course, here, like, everyone will be different because you all have different masses. But as I mentioned on the website, I want you to do it for a given mass so everyone can sort of check their answers, right? Okay, so if you don't have any other question, let's start this. So now we're going to do a new unit. So now it's going to be work, energy, and power. So energy and power. All right. So this is a crucial chapter section because at some level, energy is more important than Newton's laws of motion. Newton's laws of motion do break down, especially the second law in particular here, does break down at the atomic level. You know that you have to use quantum mechanics to understand what happens at molecular level, at the atomic level. You cannot sort of apply Newton's laws of motion to understand how an atom works. All right. For the very, very, very large, Newton's laws of motion also, like second law, may fail as well. You have to, well, the law of gravitation here, as conceived by Newton, has to be changed a little bit. Okay, so you have to deal with what is called general relativity. So there's limits on how you can. There's a limit, the range over which you can apply Newton's second law. However, energy, as far as we're concerned, is valid from the smallest to the largest. So we've never come across a case where energy is created or destroyed. This is something that you've learned from elementary school. So energy is neither created nor destroyed, but merely transformed. Okay. All right. So let's start with energy here. If I were to give like a rough definition of energy, energy is the ability to do work. All right. All right. Well, this definition doesn't help us very much if we don't know what work is, right? So you can sort of think of work, of course, in an intuitive way. If I want to lift my stapler, I need to apply a certain amount of force over a certain distance, and I'm doing work. Not a lot of work, mind you, because it's very light, but I'm doing work. So that's an intuitive concept of what work is. Now, of course, as physicists, we give a very, very defined definition of work, and work will be as defined as follows, guys. So work by a force F is defined as, so first of all, the sample for work, it's W, a big W, not a small. Small W is weight. This is a big W. And it's going to be what we call the dot product of the force times the displacement of the point of contact. So this is very important here. This is a displacement of the point of contact of force F. So once again, if you want to interrupt me, just give me a shout here, because I don't look at my screen all the time here. Point of contact of force F. All right. Now, have you guys in math, I guess HL, probably might be SL, you might not have learned this. In HL math, have you learned like dot products or scalar products? Hands up?
I don't think so.
You don't? No, what are you doing in math? Okay, so you haven't, okay. So you're gonna learn, this year you're gonna learn one type of products. You've learned how to add vectors. You've learned, no, I didn't teach you how to subtract vectors. I don't think so, did I? No, I don't think so. I don't quite remember. But anyway, you've learned how to add vectors. Now, this is one where you multiply vectors. And you're going to find out here that there's two types of multiplication, unlike scalars when there's only one type. Here with vectors, there are two types. This one here is called the scalar products because it outputs a scalar quantity. So work is scalar. There's no direction. Energy is scalar. Power is scalar. So there's no direction associated with any of these concepts. So this is called a scalar product because it spits out a scalar quantity, which is work. This is also called the dot product because there's a little dot there, right? So you can see here is a little dot. The other one that you're going to learn next year, or you're going to learn hopefully this year too, in HL at least, it's called a vector product or cross product. So cross product is a product between vectors that spits out a vector quantity. So you're going to learn this for sure next year in grade 12 physics. Okay, so what does it mean here? This is what it means. So it means the vector product is the absolute value of both. Okay, so you take the absolute value of both vectors times the cos of the angle between those two vectors. All right, so theta is the angle between those two vectors, between the force and the displacement of the point of contact of the force. Now, to keep it like very simple here, right? I don't put like the absolute value, but you have to understand that you don't put any signs here, right? So you don't put any signs for F or delta T. The sign will be taken care of by the cos, right? Taken care of by the cos. So this is the definition of work by a force. All right, so let's look at some of those things here. Let's look at cases where the work done by a force will be zero. I guess you can see me here. I'm going to sort of move back towards the wall. All right, and let me see here. It's very hard for me to see. Okay, I'm pushing the wall here. I'm pushing the wall. Now, if I'm asking you, am I doing work on the wall? Raise your hand and share. Am I doing work? Yeah, Max. It's always Max. Okay, other people have to raise your hand too. Yes, Max.
But there would be zero work because the distance is zero, and so you multiply it.
How many?
That's correct. So
questions
mute.
did she give you?
Make sure you mute your. Anyway, there seems to be some feedback.
15.
Yes, can mute, guys. If you don't raise your hand, mute your audio. Okay, yes, there's no work done by me on the wall because the point of application of contact of the force is zero. Delta D here, delta D, it doesn't matter if I sweat, right? Right, delta D here is zero, so there's no work done by me onto the wall, okay? No work done by me onto the wall. Okay, let's look at another case here. All right, so I'm moving this iPhone, right, at constant speed, right, in the horizontal direction. Now, if I ask you, what is the work done by gravity on my iPhone? What's the work done by gravity on my iPhone? It doesn't have to be going at constant speed, right? Eric, Hugh?
Zero.
Zero, why?
Because cosine 90 is zero.
That's correct. The force of gravity, so in this case here, okay. By the way, whenever I put something in orange, you don't have to take notes of this, right? So this is like my iPad here. Of course, this gravity is coming down, and the point of application of the force of gravity is right here, and it's like this, all right? And what you notice here that the angle is 90 degrees, and cos of 90 degrees will give you zero. So when the force is 90 degrees perpendicular to the point of displacement of the point of contact of the force, this is zero, okay? This is going to be exactly zero. The normal force, well, the force provided by my hand is also, I'm not doing work at all because the normal force is 90 degrees perpendicular to displacement, okay? The normal force actually never does any work. All right. So normal force never does well for the most part. I mean, there are some cases where yes, it does work, but for the most part, the normal force does not do any work because of two reasons. Either delta D doesn't is equal to 0, or the forces are perpendicular to the direction. Okay. All right. Good. Okay. So let's do a simple example here. So put it back to black. So example. So a box, a 20-kilogram box, is pulled at an angle of, let's say, 60 degrees with the horizontal. With a force of, let's say, 160 Newton. The box moves horizontally on a rough surface, surface plane, exerting a frictional force of, let's say, 30 Newton. All right. All right, so let's have this here. So we have our box right here. Oh, the box moves, let's say 15 meter. Wow, that's a lot. Okay, let's say 5 meter. All right. So here's our box.
Sir.
Yeah.
Can you let Matthew in the Zoom meeting, please?
Should I? Thank you. All right, so here's the box. And then someone is applying a force. So we're going to call this the applied force at an angle of 60 degrees. There is friction. And this friction, of course, will be kinetic here. All right. So let's have like our axes here. Actually, no. Yeah, that's a good point here. The good thing about this is that work energy, you don't have to care about directions anymore. And that's why we love energy so much, because it's a lot easier to work with scalars than to work with vectors. Vectors, you always have to care about the directions. You have to split it into X and Y axis, Z axis, and so on. With work and energy, no such thing. You care only about numbers that are scalars, no directions. All right. Okay, but nonetheless, I will sort of do an FBD. So this is your box here. All right, and it's going to be the displacement of the box. All right. Now this is our still FA here. The friction is still there, and so on. All right. So that's the situation here. It's a bit laggy. You can see here on mine. Okay, so A. Find the work done by the applied force. To find the work done by the applied force. Should be horizontal here, right? It doesn't look horizontal here, but horizontal. Okay, so what we're gonna do here, we're gonna do so what we'll do is we're gonna use the applied force, right? So this is the applied force right here. And what we're gonna put, we're gonna superimpose the displacement of this applied force. Well, you can see here that the displacement of the applied force will be in this direction, will be the same as that of the object, right? And what is this angle in between? Well, the angle will be 60 degrees, right? Well, this is all what we need. The work done by the applied force, which I will sort of call like WA, is equal to the applied force times the displacement of the applied force times cos of the angle in between. Now, the applied force, the displacement of the point of application of applied force is the displacement of the box. Now, for most, for grade 11, like the displacement of the object will be equal to the displacement of the force being applied onto it, okay? This is not always true. Actually, this is not true in most cases. But for grade 11, we're gonna sort of stick with this. It has to do with the fact here that in grade 11, we consider object as being point particles. Of course, they are not point particles. They have a certain extension in space. They have a certain volume. They distort too, they deform, but we don't take this into consideration, right? So for instance, if this box were made of a kind of stretchy material, if I pull on it, you can appreciate here that the distance of the point of application of my force will not be exactly equal to the displacement of the center of this stretchy box. It will be a rubber, so it would be like different, right? But now what we're doing here, that whenever we do physics here, we just always assume that the object here, the 3D object, is super rigid. Just think of it as a point particle. All the mass is concentrated in one point. And this is why I ask you like to do an FBD to put a little point. All right, this is what it symbolizes. Okay, so let's continue here. So it's cos of 60 degree. So it's just a question of putting like the units. So it was 160 Newton times 5 meter times cos of 60. What's cos of 60, guys? Is it half or root square of 302?
Half.
Half? Okay, so half. I trust whoever. Okay, so it'll be like what? Is it like 80?
I'm
Is it
sorry,
like 400?
see what you're writing.
What's that?
I can't see what you're writing.
Yeah, that's strange. Huh? It doesn't appear. Very good. Okay, it happens to me like my previous course too. So what I'll have is I'll stop sharing and I'll share it again. I don't know why it does this. So I'll share again. I don't know if there's a time limit for the sharing. Okay, so you should see it now. Everyone sees that?
Yeah, it's good.
It's good. Okay, so is it 400, guys? Is this 400?
Yes.
Yeah, okay, so
Yeah.
400. Now you notice here it's Newton meter. Well, Newton meter is nothing else but joule. So the unit of work is the same unit as that of energy, and it's not a coincidence. We're going to find out a little bit later why, okay? So the unit of work is a joule. It's Newton times meter, not per meter. Newton per meter was the spring constant, remember? So this is joule. Very good. All right. So let me put this a little bit up here. All right, the next thing here is the network. The network done on an object so I'm going to call this like WNet. So network done on an object is the addition of all the forces acting on the object, all right? So scalar addition of all work.
Oh, sorry, sir. Work is uppercase W, right?
Yes, always.
Oh,
Yeah.
okay, sorry. I thought
Yeah.
you said lowercase.
This is my like small one here. All right. So that's lowercase, that's weight. So yeah. So scalar addition of all work done by all work done by forces on the object. So in other words, it's equal to this, right? Work done by the first force plus the work done by the second force plus the work done by the third force plus whatever it is, okay? And so this is also can be written as this, right? So remember here, this means like this means the summation here. So it's the summation over all the work, okay? So next work done is a scalar addition of all the work done by forces on the object. Okay. There you go. All right, so let's do this one here. So B, well, I'll just do it here. So B, find the net work done on block. So remember the block is this here, right? So now we're going to find the net work done on this block. Okay, so when you're looking for network, what I would suggest you do, just do it, is to draw an FBD. All right, so let's draw an FBD of this block here. So we have FA like this. We have, we have the friction. we have the normal force, and we have the weight. There we go. You don't have to put the direction, like, it's fine, okay? Direction that this object is moving. And then on top of the FBD, what I want you to do is I want you to put the displacement vector. So in this case, it was like this, right? So on top of the FBD, you're going to put the displacement. And as I said here, always consider like the object is moving like a point particle, okay? So this displacement here will be the same for all forces. All right. Now you can find this. So this angle here, once again, it's 60 degrees, right? So the net force on this object is as follows. It's the work done by all the forces. So it's going to be the work done by the applied force that I'm going to call A. The work done by friction, which I'm going to call like W with little f, plus the work done by the normal force, which I will call N, and plus the work done by gravity, which I will put G. So it's the work done by the applied force, the work done by, whoops, the work done by the applied force, the work done by the friction, the work done by normal force, and the work done by gravity.
Wait, sir.
Yeah.
So for this, so when you have like, so how come like, so you don't like put like direction is like positive, and
No,
so
you
you won't
don't.
have.
That's what I said. The work is a scalar quantity, so you don't need to put these.
Oh, okay, so it's not minus weight, minus work of the
No,
gravity.
no,
Okay.
never.
Okay.
Never. Okay, so before we move on here, is there terms that we know, like that we know right away, like without calculation?
So
You raise your hand, guys. If it's Max again, I'm gonna choose someone else. So is there any term here that we know? Oh, the problem is I cannot see it. Okay, yeah, Day, yeah.
so your normal force and your gravity, so the work of the
Yep.
normal force and the gravity is 0 because they're perpendicular to the direction of
Very
the
good. Excellent. Excellent. Absolutely right. So here, whoops. I don't know if I can undo. Anyway, I'll go over it. All right. So this one is 0 because either Fn is perpendicular to delta D, or the displacement upon of contact with normal force doesn't move. In any case, here we'll just put this here. We'll just put like Fn is perpendicular to delta T. It could be also because like the point of application normal force doesn't move at all. Okay, and gravity also is 0. That's correct. All right, 0 because the gravitational force, which is this one here, right? That's the gravitational force here. Weight is nothing else but gravity. Is also perpendicular to the displacement. Very good. So in this particular equation here, the normal force and the gravity doesn't do any work whatsoever. All right, so now we already computed this, so I can put like the value, but I'm not going to put the value yet. Okay, so this one here is what? This is going to be the work of friction times the displacement times cos of theta f. Theta f is the angle between friction and the displacement. Can anyone tell me what this angle is? Okay, Aditya?
180.
It's 180. Absolutely. Very good. Excellent. So you can see here that this is the angle here. It's always between the displacement and the friction, sorry, the force. So in this case here, it's 180. Excellent. Right? It is 180. And what is cos of 180, guys? Anyone? Yeah, day again.
-1.
Yeah, -1. Absolutely, yes. So let's put this here. So WA plus friction times delta D times cos of 180 degrees. I don't know if it, there we go. And this, of course, is -1. So you end up with this. So work is a scalar, but it could have a positive or negative value. So work done by a force will be positive if the angle is anywhere between 0 and 90 degrees. Of course, 90 degrees is 0, right? The work done by force will be negative if the angle is between 90 and 180. It's going to be negative. Now, work done by dissipative friction, you remember bad friction is always negative, okay? If this were traction, if friction were traction, it would be like positive because traction is the same direction as the displacement, right? Okay, so now we're ready to find the net force. So what was it again? Well, I don't remember what it was. What was it? 400, right? 400 joule. So 400, whoops, 400 joule minus was my friction. I'm going to move this around here. It's going to be a little bit slow on yours. What was my friction? How much friction did I put on there? 30. Okay, so I put 30. 30. So minus 30 Newton times 5 meter. So notice here for the well, okay, it's coming. I can see it's slow. All right, come on. There we go. I can see here I don't, yeah. So you can see that the force and displacement is all absolute value, right? The sign will be taken care of by the cos. All right, so 30 will give me like 150 joule. And so 250, whoops, 250 joule. So this is the net force. All right, very good. So once again, the net force on an object is the scalar addition of all the work done by the forces on this object. Okay, and as I said earlier here, you should, let me put it this way here. So what I would suggest you do is do an FBD and then put also the direction of motion, direction of displacement, the vector, displacement vector on top of the FBD. And then you can sort of figure out your angles. Okay. Okay, any questions? All right, so what do we have? 11, 16? Okay, so warning. The network is not the work done by the net force. Okay, so the net work is not the work done by the net force on the object. It's the addition of the work done by each force. It so happens here that if we were dealing with point particles, that would be the same. If things were only point particles, little point forces, then the net work would be the same as the work done by the net force. But in general, it's not the case. Okay, so we're going to come back to this like next year. Okay? So I'm going to call it this. This is actually the work done by net force is actually called the pseudo force, pseudo work. But anyways, we'll talk about this like next year. Okay. All right. So let's look at another topic here. So remember, like energy is the ability to do work. All right, so let me introduce you to the first concept of energy, and it's called kinetic energy. Now, in your book, kinetic energy is given by EK. This is my K. This is my K here, right? I don't like to use two symbols. I prefer to use one, and it's going to be big K. Easy thing. The reason why I like this is because sometimes I'm going to put like subscript, right? I'm going to put subscript here, and I don't want to have like another subscript in the way. All right, so, and this is also customary in most physics textbook worthy of their name. All right, so kinetic energy is the energy possessed by an object by virtue of its speed. All right. So kinetic energy is the energy possessed by an object by virtue of its speed. What does it mean by virtue? Because it has speed, it has kinetic energy. That's it, right? Okay. So I'm gonna stop like sharing. Don't worry, I'll come back to it. Okay, come back to it. All right. So let's look at this here. So you have to use your imagination here. Okay. So let's say you have a watermelon in the middle of the road. Or perhaps like, let's say you have like someone is making a sculpture in watermelon of someone, right? The person, he puts it in the middle of the road, right? So he assembled like different like watermelons, and then he put this in the shape of a person, put this in the middle of the road. There's two cases. First case, you have a truck coming at a speed of 100 kilometers an hour. That's case one. Case two, you have a bird, and this bird is also going at 100 kilometers an hour, right, in the middle of the road. So two is the bird, and one is the truck. Now, if I ask you, which one of the two, case one, the truck, or case two, the bird, which one would have a greater ability to destroy the watermelon? Is it going to be the truck, or is it going to be the bird? So I'm waiting for, okay, Madav. Okay, hold on a second. Okay, some more people. All right, so yeah, what did I see here? Eric Hugh, yeah. Eric,
the truck.
The truck, why?
It has more kinetic energy.
Why?
It has a greater mass.
That's correct, because it has a greater mass, right? First of all, in order to destroy something, you need to perform work, right? You need to move, you need to exert forces, right? And move those pieces apart, right? So you're actually doing work. And remember, like what we said, energy is the ability to do work. So in order to destroy something, you need to apply a certain amount of work. So there should be some energy there, right? And in the case here, of course, the truck has more energy, has more greater ability to destroy the watermelon than the bird because the truck is more massive. Very good. Okay, so now we're exploring here, like what factors affect kinetic energy. Okay, case one, same thing, like the truck. Case two, the bird. No, sorry. In both cases, case one and case two, it's the truck. Okay. So first, the truck is coming towards this watermelon sculpture at 100 kilometers an hour. Case two, the same truck is coming towards the watermelon at a speed of, let's say, 1 kilometers an hour. Now, if I ask you again, so in which case, Max is on your, he likes to go ahead. Okay, so if I ask you in which case, will there be a greater ability to destroy the watermelon? So case one was going at 100 kilometers an hour, or case two when it's going at 1 kilometers an hour. Okay, it's always the same. I want some other people, not always Max. And okay, so who's this? Forrest, yes.
Case one, because it has a greater speed.
That's correct. Okay, so you got it good. So of course, like it has the same mass, but it's going faster, so it has a greater ability to do destructive work. It has greater energy, and because it's moving, we call this kinetic energy. So these are the two factors that comes into kinetic energy, mass and speed. All right, so let's go back to sharing. All right, so let's see here. All right, good. So what you've seen here is you've seen that kinetic energy depends on the mass, depends on the speed. Now, it took a couple of years for physicists to figure out the right relationship, but it's pretty easy. Well, it's pretty easy. No, it took like a couple of years. Okay, so the kinetic energy is equal to the mass times the speed square. So that's the formula for the kinetic energy. Okay. So the kinetic energy is proportional to the mass and proportional to the speed square. So what does that mean? It means that for an object going at the same speed, if you double the mass, the kinetic energy will be double. For an object of given mass m, if you double the speed, how much will the kinetic energy change? Waiting. Okay, some other people, always have the same people. Okay, Leo Tang, there we go. Leo?
By factor of 4.
Yeah, factor of 4, excellent, right? That's ratio, right? So you double the speed, kinetic energy goes up by a factor of 2 square, which is 4. Very good. Now I'm going to let you like figure out here or just verify that if you put the units in, you're going to have kilogram meter square per second square. Now, if I put, okay, so I'll put it here, but you don't have to write it down. Okay, I'm going to put it here, but don't have to write it down. So the unit will be this: kilogram meter per second, meter square per second square. Now, if I put this like this, what you notice here, this is a unit of Newton, right? It's mass time acceleration. So Newton meter, so it gives us joule, as it should, right? So because kinetic energy is energy, and energy is measured in joule. All right. Okay, so I'm going to leave you with the last one. Going to be this. It's called the work. It's called the work energy theorem. Yeah, let me write it like better here. The work energy theorem. Does anyone know what theorem means? Anyone? What does, yeah, Max?
Is it like a prompt that has been supported by a lot of evidence
Okay.
and is considered true?
Yeah, like there would be like a law here. All right, a theorem that it deals with math, right? A theorem means it's a consequence, a mathematical consequence, given some premises, some mathematical premises that we know, and then we use like logical connections to put them together. So that's what a theorem is. So it's a mathematical truth based on truth premises. Okay. So why is it called a theorem here? Because you're going to see a very first relation between work and energy. It's called a theorem because if things were only point particles, you can derive it. You can derive it mathematically, but it goes beyond this. All right. So we'll learn this in grade 12. So the work energy theorem tells you the following. Work energy theorem tells you that the net work done on an object is equal to the change in kinetic energy of this object. So this is what it tells you. All right. So the net work done an object is equal to this. Now you remember, okay, let me see myself here. All right, good. Remember if I push this, right, I'm doing positive work, right? The force is in the same direction as a displacement. I'm doing positive work. There's no friction, the normal force from my hand, and gravity doesn't do any work. So here what happens here is that the net work is the work done by my hand pushing this, and it's going to be positive. And if it starts from rest, you can see here that it's going to pick up speed. This is exactly what it says right here, right? So what it says right here, it says that if the net work is positive, then this is going to be positive. So that means that the final kinetic energy will be greater than the kinetic energy. So positive work will help to speed up an object. In contrast, if I move, I'm not going to move this. I don't want my iPhone to fall. But if I push this, all right, and let go, it will come to a stop. It will slow down. It will be a high speed, and it will slow down. It will slow down because there's friction, and we know that friction, the work done by friction is negative. So once again, if the net work done on an object is negative, the kinetic energy, the initial kinetic energy, will be greater than the final kinetic energy. Usually the mass stays the same. So what will change is the speed. All right, so let's put this here. All right, so when this is greater than 0, therefore this is greater than the final kinetic energy is greater than the initial kinetic energy. So that means that the final speed is greater than the initial speed. So it helps to speed up an object. Whoops, doesn't look like a up, look like a up, up object. In contrast, whoops. In contrast, when the network is negative, then the final kinetic energy is smaller than the kinetic energy. Therefore, the final speed is less than the initial speed. Therefore, it helps to slow down. Slow down object. All right. So positive work helps to speed it up. And when I say helps, it's a bad word. Yes, Madav.
In this equation, we're then like never gonna have the mass change for an object, but we're gonna have the kinetic energy change based on its speed.
Yeah, yeah. Usually the mass doesn't, I mean, we're not doing like particle physics here. So usually the mass doesn't change. Yes, it's always going to be the speed. Yeah, the helps is not a very good term here, because what does speed up, what does change the acceleration of, this velocity of an object is really the forces, right? But when the network is positive, then it means that the object speeds up, okay, when it's negative. All right. Okay, so let's do a very simple problem, and that'll be it. So C, so it all goes back to the same example. This, remember this block, 20 kilogram block. And then what we're going to do here is this. If the block starts from rest, so find its speed after traveling. How much did it travel, guys? 5 meters? Is that it? Was it 5 meters? Yeah, Dave, you,
Yes.
yeah, Dave, okay, thank you. 5 meters. All right, so I understand that here, you can do this problem. Yeah, thank you, Madav. Thank you for the thumb up. I know that you can do this using Newton's laws of motion. I know that. But if you use Newton's laws of motion, here you will have to use direction, you will have to do this, and so on. You're going to find here that it's much easier to use like energy method. So this is called energy method. So what we're looking for, of course, we're looking for the final speed. Where's the final speed contained in? Well, it's contained in the final kinetic energy. So since we know the mass, if we find the final kinetic energy, we'll be able to find the speed. Of course, what we're going to do is that we're going to use work energy theorem. So using work energy theorem, so once again, the net work done on an object is equal to the change in kinetic energy of the object. So we're going to put like Ki on the other side. All right, so the final kinetic energy is equal to the initial kinetic energy. Well, there's one term right away that we know it's zero. It's this one, zero, because the speed, it starts from rest. Right? So what do we have? We have the final kinetic energy is equal to the net. What was it? Was it like 250 joule? Was it this?
Yeah.
I think, yeah. So, okay, so now we just isolate for the speed. Don't forget, it's only the speed that is square, not the mass. So since you're all old professional here. We're going to bring the 2 up. We're going to bring the mass down. We're going to take the square root. Now, notice here that when you take the square root, you always have positive, negative. The kinetic energy doesn't matter the direction. It's only the magnitude. So don't put like a plus minus, just put plus. Okay, it gives you only the magnitude. So it's going to be like 2 times 250 joule divided by the mass. I don't remember what the mass was though. What was the mass?
20 kilograms.
20 kilograms. Okay, so, oh, no, it's good. Actually, that's pretty good. I use those numbers out of my head, right? So it gives you 25. Oh, look at that. Beautiful. Oh, by the way, so if I do this like a little bit more, if I look at my units, but okay, so I'll just show you with the units. So remember here that joule is also kilogram meter square per second square, right? Divided by 20 kilogram. So you notice here that the kilogram and kilogram will cancel. And then you'll be left with meter square per second square. And of course, root square of meter square per second square is meter. So there we go. So now it gives 5 meter per second. Beep. There we go. All right. Yeah, thank you, Max. I don't see everyone does that. Yeah. Okay, so any question?
Yeah, can we scroll up from the very top because I was doing my French oral?
Yeah, I will.
Okay.
Later. Just I'll do that.
Okay.
Any questions here beside this?
Did we reach a conclusion about the Wednesday, Thursday, 2 times a day thing, or once
No,
a week?
I didn't send the Google form yet. I will do that perhaps like tomorrow. Right. So for now, we'll meet again like tomorrow, like at the same time, 10:30 on Thursday as well. Now for Tuesday, we might have to change it because apparently like we'll talk about this. All right. Oh, it says my internet connection is unstable. Can you still hear me, guys?
You lagged out a second ago, but it's fine now.
Oh, okay. All right. I will, for those of you who were late, I will sort of show you the notebook here in a second. Okay, so if you don't have any other questions, so make sure you look at my website. Just do the problems in the textbook regarding this, and then we'll meet again tomorrow at 10:30. Okay, guys. And for those who wish to look at the notebook, you can still remain online. And if you want to ask me personal questions, then you can do so. All right. Until then, well, I'll see you tomorrow and take good care. All right.
Bye, sir.
Bye-bye. Bye. Okay, so let me share the screen again here.